Hello everyone, it's Dr. Liu. Today I'm going to show you the third step on development of a robot simulator supporting OPC UA using Python, VTK, and WX Python. And this step is to prepare robot 3D model in STL format. How do we do that? Step by step. First, we need to download a FANUC 60IB robot 3D model. That is a free data you can download from 3dcontentcenter.com. You may need to register in order to download it. Then search the Google looking for this robot specification data. I found it from this link. You need this datasheet in order to figure out what is coordination offset between robot each joint. And third step is use any CD software, Creo, SolidWorks, Solid Edge, Inventor, or FreeCD in this case, to disassembling the robot model and save each joint as a separate STL file. You may notice after you save them as a separate STL file, the coordination orange is not at the center or rotation center of the joint. So it is necessary to use that software to translate the coordination orange to the rotation center, and that will be very helpful for the following model assembly in the VTK environment. So in the following steps, I'm going to show you how do we do this. So here's the website, 3dcontentcenter.com. You need to register and log in order to download the data. So you input the FANUC robot and you search it. You will find the FANUC 16IB robot from here. And then you click it. It will open the detail of this robot. Select the model format we're going to use. In this case, we use step mode, step format. Then you can download this model and save it in a folder. So in this case, on the My Project folder, I save it on the FANUC 16IB model. Next, we search Google and looking for this robot's datasheet. I find it over here. You can download it. The first page is not important. The second page showing you the robot dimension, each joint rotation limitation. For example, the J1 can rotate 360 degrees, J2 250, J3 460, and so on. Other data we need to pay attention is the offset between each joint, those value, 525, 770, 150. So the robot coordination system is this direction is X, towards the in its Y direction, and the top is Z direction. It follows the right hand convention. So we need this data to figure out what is coordination offset between each joint to the base. By looking at those data, I find out all those offset and save it in a txt file. So assuming the base is J0 and the J1 is here, which X, Y offset is 0, Z offset is 245, which is the height of this base. With that one you can find it from the model. J2 is here. As you can see, X direction offset is 150. Y has no offset because they are in the same position, but Z is 525. So that's why J2 corresponding to J0 base, which is X 150, Y0, and Z will be 525. For J3, which is here, This is J3. Again, X offset is 150, Y is 0, and the Z direction is 525 plus 770, which is 1295. Use the same approach, you can find out J4 offset to base, J5, J6, and J7. Those data are very important. We will utilize it later when we assembling the each joint in the simulation environment. And then at this moment you will have model, you got a data sheet, and next step is we are going to manipulate those data. Now let's open this robot model in a CD environment, in this case FreeCAD, and then use this software. You can select each joint, and export the joint as STL file, which I already did. So for example, for joint 0, you just give a name, save. Same thing for joint 1, export, give a name J1, J2, J3, J4, J2, J3, J4, J5, J6, just do the same. So after you've done that, you have all the joint STL file saved over here. So one thing you will find out is, if we open one, for example, you know what, let me create something just for testing purpose. So I'm going to save this one as a different name, export as J0 test, for instance. Okay, so I have a file called J0 test. Open it. So remember, as I said, the coordination orange is not at the center of the model geometry. So here is the geometry center, and here is a model. See, they are so far away. So we need to translate, move the model to the center, move the model center to this origin center. In order to do that, keep this selected, click model, in this 3D scene environment. So the red color indicate X direction, green color indicate Y direction, and the blue indicate Z direction. So first let's move in the Y direction, which we need to move in the Y minus direction, minus, I roughly know the number, so minus 11,000. So it's moved to here, and the X, you need to move in the X plus direction, which is 2240. Okay, and let's look at it from the top. Okay, it's not in the center yet. Let's keep moving. So we continue in the X plus direction, move to 4, a little bit too much, 3, yep, 3, maybe 3, oh, 2, 3, yeah, so that looks about right. And in the Y minus direction, we need to move more in the Y minus direction. Remember that is 2, 2 or 2, 1. Yep. So you can see this is pretty much in the center. And in the Z direction, front, I want to move to here, which is Z. I need to move the model to Z plus direction, which should be 90, about 90. Okay, now we are good, and select the model again and export as so each model save into another folder. In this case, you see J0A, J1A. So basically, the center. You move the model to the model's geometry center to uh, the the origin center. Just here in this case, for testing purpose, I'm just say okay, move to A, B, C, whatever. Okay. Now if we close this one, and if I open A, B, C again, now if I say transformer, you see my model geometry and the coordinate center, they are together. Okay, so do the same thing for all others, which I have already done. I save everything in this center folder. For example, let's see the J1. This is J1, and that is where the model center is. This is not necessarily is a final rotation center, which you need to do further. That's why I save it in the geometry center first. Then you need to rotate it, move it further, which I save everything into another folder called Phalanx 16i new. New means this STL, those model, the coordination is at the joint rotation center, which is much better for final usage. For example, J1B, as you will see, this case, you see, it's no longer in the geometry center, it's at the model joint rotation center. Okay. Of course, you can just one shot move from the original position to here. I'm just do this in two step. That's what I did. So do the same thing for all other. Let's pick up this one. For all other joint, for example, this is joint 2. Yeah. So here is joint 2 rotation center. The geometry center is here, but the rotation center is here. So what we really need is rotation center. Okay. So now at this point, you will have the robot model, the joint original model, the geometry center, and the final STL model, which we're going to use in the robot simulator software. And then here is the joint offset, which I got from the robot datasheet, specification datasheet, which we're going to use later. So this is a short summary of all the STL model files. The initial model, the disassembled original joint model, origin centered joint STL, and the finally updated robot joint with joint offset. Now when the robot simulator starts, it will load the STL model of each joint, which we created one by one. from J0 to J6. So J6 and J7. So J7 actually means the gripper attached to the J6. And it will use the offset, joint offset data to assembling each joint into the correct location. And we now know that this joint offset is extracted from the robot datasheet, which we did before. Now let's look at the code in the Python on how we assembling those robot joint in the VTK environment as a robot. So let's briefly review, the VTK pipeline programming, which I already showed in the previous video. So in this study VTK Python, we are going to load just one joint into the VTK environment. According to the VTK pipeline, you need to first create a reader object, load the STL file in this source, set this source to the mapper, data mapper. You create the VTK actor, you add the mapper, set the mapper to the actor, then you create a render, create a render window, add the render to the render window, then you create a render window interactor, you set the render window to this RIN object, then you add the actor to the render, then you start render window interactor, and you will see the first joint, robot joint that we loaded, and you can interact this model in the VTK environment. So to load the entire robot into the VTK environment and assembling them together is pretty much same as this project, except you need to make sure they are in the right location, and you need to add some other support function. So first let's look at how it looks like if we assemble the robot together before we look at the code. So this project has two steps. First step is load each joint one by one and assemble them into the right location in this VTK environment. And then second step is if we click OK, it will test J1 rotation, J2 rotation, J3 rotation, J4, and so on. Don't worry about it right now, their rotation is not correct because we didn't set up the rotation limit yet. Alright, now let's look at the code. This portion is same. First, we create another object called colors. We want to give each joint different color, so we want to use this one. Then you create a render window, render window interact. This is pretty much same as this Python code. Then we also create the origin axis, which display where the base is located, which is a source that VTK provided, a coordination source. You set the scale, create the data mapper, and attach it to the mapper for the source. Then you create an actor for this axis called axis orange. Set the mapper to the actor, set the position, which is the base. Then you add it to the render. So that is the preparation. And start from here, we are going to load the joint. So we need to prepare the joint resource. Each joint will have so each joint will load from different files. So we create a list, and then for the joint list correspondingly we have the map list, and then correspondingly we have the act list as well as axis, because we want to display the local axis on each joint. Don't rubber the center for now. in order to generate the different color for each joint, so we want to use some random creation function. So here is the offset that we got from the robot specification datasheet, if you recall this text file. So this listed the base offset, the J1 offset, J2, J3 until the J6. Then we use a for loop to load each joint one by one. First, we create the reader object attached to the robot J list, and then we set the file to filing 16i underscore j. So if I equal to 0, which means j0b.stl, so you load the base. If I equal to 1, you load the j1b.stl, and so on. So this is just some string operation. So with this step, we create the source. Then same thing, we need to create the data mapper attached to the map list. We set the source output to the mapper. Then we create the actor attached to the appended to the act list. Then we set the mapper to the actor. Then we give it set a different color for this actor. So each joint will have different color, so we can distinguish. Then we add the actor, the joint to the render object we created before. Then we set its position to its offset position. For example, if I equal to 0, which means we set the base. If it's I equal to 1, we set the J1. So this is how we assembling each. You just do this loop. You will load each joint model STL file, create the actor, and put them in the right location. In addition, we will create another actor for axis, because we want to display the local axis for each joint, which is pretty much same thing. You add this actor to the render, you set a mapper, add them location to the right location, set the scale, which is to display the length of the axis. So loop 6 times, you get everything set up. Then in order to indicate anytime where is a coordination system, we also use orientation marker wedge from the VTK. So we create create a global coordinator marker, indicate what is x direction, y direction, and z direction. So after that, you just set up some VTK, camera angle, view angle, and run the render window render. Then pretty much you get all the display which we saw before. So next step is I set up pop-up message. If you click the OK button, we're going to rotate each joint just to test the joint rotate is at the right location. So it's straightforward. So first one is test the J1 rotation. Use a for loop. Theta is rotation angle, and if we rotate every 1 degree, we rotate 1. So we need to rotate 360. So that is a loop. Then you call this joint 1 rotate z, because we are rotate surrounding the z-axis 1 degree. You need to rotate 360. That will be 1 cycle. And then when you rotate 1 degree, you need to call this render function once. So this will rotate very slow because it rotates 1 degree once. If you want to rotate faster, like for J2 until other joint, we rotate 10 degree, so we only rotate 36 times. It will be rotated much faster. So for J2, we rotate surrounding the y-axis and for GF4 it will be x-axis, and so on. And by the end, you just call that render window interactor start. So here, why I do this? Because now you maybe remember why I need to move the joint model to its rotation center. That is to verify their rotation correctly. If they're not, then the programming will be quite challenging. So that is pretty much the code we use to load the model each joint into the right location and test each joint rotation. So to test the developed robot simulator, I also prepared robot simulation environment in the Visual Components. And in order to do that, we need to import the downloaded Final 16 IB robot into the Visual Components environment. And this, how to do that, can refer to the Visual Components Academy tutorial. And the second step is use VC model plus the TwinCat OPC UE extension. We make this VC environment to work as a robot OPC UE server. We can use that to test the developed robot simulator. In the previous two videos, I already showed that. Maybe I will create another video to show you how to use VC to model the robot and how to add the TwinCat PLC and link that TwinCat PLC to the VC environment through OPC UA and create a OPC UA server which we're going to use to test this robot simulator. This is the end of this tutorial video. Please check out above YouTube video link to see the full video of the robot simulator.